looking at section 7.3, complex numbers in polar form. You first get a chance to experience complex numbers back in your Algebra 2 days, and we did a little review of it way back at the beginning of first semester in the review chapter. But when we were looking at complex numbers in what we typically refer to as rectangular form, a plus bi. Now, real numbers we graph on a number line. You can graph complex numbers, but you have to make some changes here because complex numbers, a plus bi, have two parts. The a, which is the real part, and the bi, or just the b there, because it's times the I, which is the complex or imaginary part. And so you're going to need two axes. You're going to need an axis for the real part and an axis for the imaginary part. So as you can see in the diagrams that I've already drawn here on the whiteboard, you can see that we're going to set them up kind of like what looks like the coordinate axes. But instead of having an x-axis and a y-axis, we're going to have a real axis and the imaginary axis. So the horizontal is going to be the real, the imaginary is going to be the vertical axis. And you can see that we do the real part if we have the number a plus bi. Notice here in the graph that I have, we're going to graph a plus bi like the ordered pair AB, where a is the real part, b is the imaginary part. A is on the real axis, b is on the imaginary. We go a to the right, we go up b in this case, with the way I have it drawn, and we have a graph of what we call the complex number on the complex plane. Sometimes, and I may be wrong on this, I used to think that, it's been a while, I used to think that the complex plane might have been called like a let's see, what was it, a Cardano diagram or something like that, after a famous Italian mathematician, but I'll have to double check that to make sure. So now, we're going to graph, and I have some examples here that I'm going to show you. We're going to graph complex numbers that are in what we refer to as rectangular form. We're getting to polar here, just a second. Rectangular form, in the a plus bi form, we're going to graph those on the complex plane. So I have 4 examples. I'm not going to make 4 separate graphs, but I'm going to graph each one of these. Here's your real part, here's your imaginary part. So I have -1, 3. So 1 to the left, up 3, that would be for part A right here. This one over here, this would be, the real part is -4, the imaginary part is -2, so 4 to the left, 1, 2, 3, 4, 2 down. I'm approximating it there, and there's B. Now you say, well, this is just a real number. This isn't a complex number. Well, real numbers are complex numbers. It just doesn't have an imaginary part. It's as if you have plus 0i. So this is as graphing 3, 0, which makes sense because this is the real number line right here. That's a real number. We're going to put it right on the real number line there, what would correspond to the ordered pair 3, 0. Now this guy here, he's a complex number as well. He just doesn't have a real part. This is a pure imaginary number. All right, so that means that this is the same as 0 plus 4i. So what would make sense, it made sense here with the real part should be on the real number line. Pure imaginary should be graphed right on the imaginary axis here. So what I'm going to do here is I'm going to graph this as 0, 4. 1, 2, 3, 4. Here's 0, 4, and this would be for part D right here. Oh, this was part C down here. So it's really simple to graph complex numbers if they're in rectangular form, a plus bi form. It's really simple to graph those. Now, real numbers have an absolute value. The absolute value of a real number is the distance that the number is from 0 on the number line. As it turns out, complex numbers also have an absolute value. Okay? And it's also a positive number. But because we're graphing on the plane here, the absolute value would be this distance from the number, the point there, to the 0, 0 there, which we would correspond to the origin. So what we're going to do is we're going to have to use a little distance formula here between this point and this point, and that's what I have written down here, the absolute value of a complex number. They like Z for some reason to name complex numbers. I'm not sure of the history of that. Z equals a plus bi is the distance between a, b, and 0, 0 on the complex plane. And we use the absolute value bars, just like we have absolute value of real numbers, absolute value of complex numbers, and it's equal to the square root of a squared plus b squared. And that makes sense because if this is 0, 0, it would be a minus 0, b minus 0, and you would get a squared b squared. Now the absolute value of an imaginary number, or a complex number, is sometimes called the modulus, or sometimes it's called the magnitude. We also like to use magnitude when we talk about vectors, which we'll do later in this chapter. Okay, I think it could be called the norm, but I'll have to double check that as well. Alright, so we're going to find the absolute value, we're going to find the modulus for these two examples right here. So for the first one, the absolute value of z would be equal to the square root of, this would be negative 5, that's the real part, quantity squared, plus negative 12, that's the imaginary part, quantity squared. So this is the square root of 25 plus 144, which is the square root of 169. Oh, this one comes out 13. That was nice. If it doesn't come out to be an integer, or I should say a whole number, then what you can do is you would simplify your radical. Don't just jump right to using the calculator and writing it out as a decimal. Simplest radical form is what I was trying to think of here. So next guy up, the absolute value of z on this one would be equal to the square root of the real part squared plus the imaginary part squared. So this is the square root of 16 plus 36. This is the square root of 52. Well, that one does not come out to be an integer or a whole number here, but it does simplify because 52 is 4 times 13. 4 is a perfect square. So this is 2 times the square root of 13, and that's the absolute value of z. Again, don't jump to a calculator unless the directions tell you to. Don't jump to a calculator and approximate it. Alright, now the complex number, as I mentioned before, in the form a plus bi is said to be in rectangular form, sometimes called Cartesian form, most of the time called rectangular form, because the a and the b are the coordinates of the point A, B in the rectangular coordinate system, kind of drawn here from the complex plane, formed from the complex plane, because we have the two axes here. What our next step is to think of writing a complex number in polar form. Now remember, in polar form, when we were graphing ordered pair, or graphing points, we had, instead of xy, we had our semicolon theta. So that comes into play here as well, as we'll have like a polar distance and a polar angle to help us with this. Well, let's clear this board first.